Hi everybody, this is Phys 102 course, Chapter 29, Magnetic Induction. Okay, we learned the magnetic flux as the dot product between the magnetic field vector and the area vector, or B times A times cosine theta. Okay, cosine theta being the angle between the area vector and the magnetic field direction. Assume that magnetic field direction is given by that, and area vector is always perpendicular to the surface and given like that. As you see in this case, the area vector and also magnetic field vectors are in opposite directions so that the flux is negative because the angle is greater than 90 degrees. For the angles greater than 90 degrees, cosine theta is negative. That's why we have now negative flux here. The magnetic flux is negative for this case. But when the magnetic field is towards the area vector like that, not necessarily in the same direction, okay? So the area vector is this way. In this case, the magnetic flux is positive. So this is the first property that we have to be careful with. As you see, the magnetic flux is a function of three things: magnetic field intensity, the area of this loop, and also the angle between the two vectors. Here, if the area vector is this way, for instance, the angle between them is theta, okay? So this is for regular surface, but if we have irregular surface like that, then there is nothing else but we have to define some kind of area vector and also consider the magnetic field lines passing through this small area vector. So now this little bit flux can be defined as B dot dA here. So this little bit flux passing through this small surface element is given by that. Now by adding all these small contributions, you can cover the whole area. It means that you are integrating to get the total flux. So the total flux is just integral of d phi b or just integral of B dot dA. So this is the total flux. And according to the Faraday's law, okay, if this total magnetic flux is changing in time, okay, it is equal to minus electromotive force, which is the voltage of the loop. So this loop produces some kind of voltage, but as you see, in order to produce a voltage, some of the ends, okay, one end somewhere, doesn't matter where it is, should be open so that we can measure the potential difference, okay? We can measure the potential difference. By this, okay, there will be some kind of potential difference so that some kind of current is going to be flowing. So the polarity of this potential difference will be very important, okay? So now let's see a very simple example with only one loop. So in this very first example, we will have one magnet like this, north, okay, and the south is downward. It's a cylindrical coil, okay, coil, so that this electromagnet is obtained by passing some currents from these iron or nickel yokes. So this can be a metal. This should be a metal, but magnetized metal. So if this is to be south, then the current should be this way, okay? So the current will be this way. So I0, some kind of current is passing through this similar direction here, so that we get N and S, so that we have now the magnetic field directions given like this, okay? North and south, okay? Now it will be always from north to south, okay? Like that. So magnetic field direction will be downward. Okay, now we place to this system some kind of wire loop, okay, like this, and then we say that this is point A and this is point B. Now we would like to see if there is a voltage induced, and we connect some kind of galvanometer here to see galvanometer or maybe multimeter Okay, so today's multimeters are very sensitive, so you really don't need galvanometer, so you can just use regular multimeter to measure the voltage here. Okay, so between the 2 points A and B, we would like to measure the voltage. Now we would like to find now the current direction, but in order to determine the current direction, we have to know what is given to us. They say that the magnetic field, okay, increases in time at a rate 0.02 Tesla per second. So it means that dB over dt, since it is increasing, is positive and is 0.02 Tesla. Okay? So dB over dt is positive. In this case, if dB over dt is positive, the magnetic flux is also positive because the area of the loop that is made by this circulating wire is not changing, and also the angle is constant. Okay, so probably the angle between the magnetic field and the area vector are in the same direction, so this area vector, so they are parallel. So basically, in order to get d phi b over dt, what we have to do is just multiply the magnetic field change in time times area times the cosine theta, which is 1. That's it. So it's just a dB over dt. So this is the magnetic flux change. So this will be equal to just minus epsilon. Okay. So this is the Faraday's law. This is Faraday's law. As you see, on one side there is a magnetic field change, on the other side there is a voltage. So electric field and also magnetic fields are related to each other through Faraday's law. Okay, so now we would like to find out the polarity of this epsilon. Now, as you see, the magnetic field is passing downward from this loop, but this loop creates its own induced magnetic field in totally opposite direction if the change in the flux is positive. Now it is the case, it's regular case. So in order to create this kind of magnetic field, so the current should pass through this way. So the current will pass through this way. Okay, so the current will go there and the current will originate from B. So it means that this will be plus and this will be minus. So it's like the battery. Always the current goes away from the positive terminal and comes to the negative terminal, so that the current direction will be like that. So induced magnetic field will be totally opposite to the magnetic field. Okay, so basically the loop is trying to get zero magnetic flux by creating its own magnetic field by this current, so that two magnetic fields will cancel each other, and then it feels no magnetic flux. So that this induced magnetic field creates some kind of potential difference. In order to pass a current from this wire, a potential difference should exist between the two terminals. Okay, good. So we know that we can get the voltage by this equation. So dV over dt is given by that, and area, they also say that, okay, the area is 120 centimeters square, and the resistance of the wire, okay, this little wire is just 5 ohms, small resistance. So by using this area, converting into the meter square, okay, so you have to multiply by this 10 to the minus 4. This is just 0.012, okay. As you see, I moved the point 4 times to the left. 1, 2, 3, 4. So it's 10 to the this meter square. So if you multiply this by that, okay, dB over dt, okay, dB over dt, you see that you get just epsilon, which is 0.24 millivolts, or 0.24 times 10 to the minus 3 volts. So this is a very small voltage, as you see. And the current is just epsilon over R, V over R, and it is 0.048 milliamperes, very small current. So we would like to really understand how the polarity of this electric field or just voltage is to be obtained. Now, suppose we have this loop here. In this loop, the magnetic field is this way, okay? the magnetic field and the area vector are always in upper direction. So magnetic field is in upper direction, and okay, B is increasing in time. It means that dB over dt is positive. B is increasing in time. So in this case, we have a regular case. If B is increasing in time, this system will create its own induced magnetic field in opposite direction, like that, so that in order to create this, the current should flow this way, so the current will flow that way. So after determining the direction of the current, you see that it always originates from plus terminal, it comes in to the minus terminal. So this will be the polarity of this potential difference, plus here, minus there. Okay, now this was for the magnetic field which is increasing in time. Now let's take the same loop again, okay? Now, again, the magnetic field lines are in upper direction, okay? But now B is reducing in time. How can we establish this? I will show you in a few minutes, okay, how we can reduce the magnetic field intensity. Okay, so if the intensity of magnetic field is reducing, there are less and less number of magnetic field lines in time, and now we have dB over dt, which is negative. In this case, the induced magnetic field direction will be in negative direction, okay? So now the induced magnetic field, because it's reducing in time, will be also create in the same direction with the magnetic field, original magnetic field. So in order to do this, using right-hand rule, as you see, the current direction will be in counterclockwise direction, like that. On the contrary to this one, okay, this is totally opposite. So this part will be plus, this part will be minus in this case. Okay, so this is how you determine now the direction of the current. From this, you can get the terminals, plus and minus, for this potential difference. Now, let's see what happens. If magnetic field is downward, like that, and B is increasing in time, okay, then we have a regular case. We have now the induced magnetic field totally in opposite direction. So in order to create that, the current should pass through this way, okay. The current is passing through that way, okay. So that if the current is passing through this way, this must be plus and this must be minus, because the current goes out from the positive terminal and comes into the negative terminal. Always this is the case. So this is the polarity of the electric field, or just the potential difference between the two terminals. Now we have another case. Now the magnetic field lines are downward, okay, but now B reduces in time. So it gets smaller and smaller in time. In this case, we have exactly the opposite case, okay, then the current will be in this direction. So that this will be plus and this will be minus. Okay, how can we increase the magnetic field intensity? For instance, we can do this by just moving this permanent magnet to the right or to the left, or just keeping this fixed and moving our loop towards, because the magnetic field lines from this is given by this, okay? So these magnetic field lines will go to find their counterparts, and they will try to bend, okay, up and down, so that now if you place the loop here, as you see, there are more magnetic field lines than here. So if you move the loop to the left, the magnetic field intensity increases, but in this time. So now it's this case. But if you move this loop to the right, it means that the magnetic field is in upper direction and it's reducing in time. It's this case. So you can do several experiments, but you can also fix the position of the loop and move this magnet up and down, or right and left. So in this case, you can change the magnetic field. Only then, if you change the magnetic field in time, then you will get a potential difference. Because according to this equation, it says that to get the potential difference, the magnetic flux should change in time. So it means that either one of these quantities can change. So what are they? The magnetic field can change in time, the area can change in time, and also the angle can change in time. So we will see how we can apply this case. But now, if we have, instead of one loop, if we had n loops, okay, for n loops, the electromotive force or the potential difference will be just n times whatever you had. So d phi v over dt. As you see, you can really have the freedom to increase the potential difference by putting more and more windings, or just turns, or loops, okay? Now let's see another example. Okay. In this example, we have electromagnet, okay, like that. Okay, so this is north side part, this is south. So the magnetic field lines are from north to south, of course. Now we put some kind of coil like this bent a little bit, and there are many, many windings, or the number of turns is just 500. Okay, so now if you look at this system, we see it like that directly above. Okay, the cross section will be like that. So this will be the cross section of the current in which there are many, many windings. Okay, so here many cables that you can see in the cross section. So they say that this is the area vector. Okay, and this plane of the circle, okay, circular loop makes 60 degrees with the magnetic field. So this is the direction of the magnetic field, but this is 60 degrees. But this is not the angle between magnetic field and the area vector, because magnetic field and the area vector is just 30 degrees. So you have to be careful with what angle is given. For this case, 60 degrees is given, but it's not the angle between the magnetic field and the area vector. It's 30 degrees, so you have to be really careful. They say that the radius is just 4 centimeters, okay, and the angle is given by that, and they say that dB over dt, in this example, dB over d is minus 0.2 Tesla. It reduces in time. So magnetic field reduces in time. Now, it means that magnetic flux, if magnetic field is reducing, magnetic flux is also reducing in time. So it's just opposite case. So, but in regular case, if the magnetic field direction is this way from this loop, the induced magnetic field should be in opposite direction if this was the regular case. But now, since there is a minus sign, the induced magnetic field direction will be also in the original magnetic field direction. In order to do this, you have to pass the current like this. So the current will flow like that, okay? It will be rotating like that. So if the current is coming like that, it's going inside the page and coming outside the page like that. Okay, so the current is going inside and coming outside. It's circulating like this. Okay, so it's circulating such that it creates a magnetic field in the original magnetic field direction. Good. So having determined that, we would like to find what is the electromotive force that is obtained between the ends. Okay, so this is the first winding starting and this is the last winding ending. So this will be just plus or minus and plus. Since the current is coming here, okay, this will be minus and this will be plus. We would like to determine what the value of this epsilon. Okay, so epsilon is just the magnitude of epsilon is just n d phi b over dt. Okay, so we just eliminated minus sign because we just getting the magnitude. So this n times dB over dt times area times cosine of angle between them. Okay, it happens to be 30 degrees. So if you put that in, now the area, what is the area if the radius is given? The area is just pi r squared. So if you put all the values there, you see that it's just 0.435 volts. So it's about 0.4 volts obtained between the two terminals of this 500 windings, okay? So if we increase the number of windings to 1000, for instance, it would be, the voltage would be twice as much. Okay, so this is the first example that we obtained. As you see, we were able to change the magnetic flux by reducing maybe this kind of current. Okay, so this current as a function of time is reducing in time. So the same, okay, this current, in order to create the magnetic field in this way, the current should be in this direction, I0. Probably the same current, because this wire, after it goes, okay, it just put there and then continuing on one circuit can drive the same kind of current. Anyway, so in this example, we obtain this very small induced potential difference. Now, let's see how we can really get a device which is very useful to be used in the development of the motors. So it's simple alternator. Alternator means that it produces an alternating current. So AC, this is alternating, okay, alternating current. So if this is not DC, direct, it's not direct current. So direct current DC, okay, IDC as a function of time is like that. It's constant, but the current which is alternating just is like that. So the current now is changing in time. Not only going to plus and minus, but also this is alternating currents. It's on plus, okay? So there is no negative part, but this is also alternating. So this is AC, this is also AC. And also there are signals which is DC plus, this is DC plus AC, because now you can consider this as DC part here, this is DC part, and this is AC part. This signal is probably I equals I0, IDC, plus some other constant I1 times sine omega t, something like that. So DC part and AC part. Okay, so having said that, we would like to create now some kind of AC potential difference by this system, okay? So now it's drawn like this, okay? So suppose we have two sides like this. This is all wire and this conducting wire. Now, as you see, now we would like to rotate the whole system like this in clockwise direction. So the rotation frequency, which is 2 pi f, is given by that. And also don't forget, this is 2 pi over t. If you need the period, this is what you have, right? Now, as you see this rotating thing, you have to get the, if this whole thing is rotating and then you just connect a cable here, they will just, okay, they will just twisting on one on another, so that there will be some kind of short circuit, and we don't want to do this. So in order to eliminate, we just put round metal rings. So this side is just touching the interior of this metal ring, and then this one is touching to the interior of this metal ring. So now these parts, some kind of, okay, these are called brushes. So this connection is called brush, usually made of carbon. So that now we measure epsilon there. So as you see, this, if there is a current, it's now coming here and then moving there and then going back and then completing the whole circuit, as you see. So this is full contact. In this case, if the whole system rotates, this rotates around this, and this part, this wire rotates around this loop, which is called the ring, okay? Then we continue getting the contact. But now the magnetic field is applied such that it's from left to right. So in this example, the magnetic field direction is from left to right, which is constant, not changing. Now, what's happening is that the area, the direction of the area vector is changing. In other words, the angle between the magnetic field and the area vector is being reduced. So now, suppose the area vector is downward here. As you see, it's now 90 degrees, so that there is no magnetic flux for this case, initial case. Suppose this initial case. So now it's totally parallel to the magnetic field, aligned with the magnetic field lines, but the area vector is perpendicular, so that there is no magnetic field. If there is no magnetic flux, then if there is no magnetic flux, then epsilon is equal to 0. This is case A. In case B, this is rotated a little bit, okay? Not necessarily 90 degrees, but it can be drawn like that, okay? So now we have exactly the same case, but the magnetic field lines now are passing through or piercing through this system. So still to the right, but now the area vector just changed. As you see, this area vector is rotated like that. So now we can draw the area vector like that in opposite direction. How can we do this? We can do it like that. Okay, so this is the area vector. So as you see, the magnetic flux is negative there. Magnetic flux, so magnetic flux is negative, but not zero. Okay, so if the magnetic flux is negative, then okay, then we have to be careful which side is going to be plus, which side is going to be minus. So as you see, the magnetic flux in case A was zero, but now it's negative. What is delta phi? So this is phi B minus phi A. So case B flux minus case A flux. Case B flux is negative. So this minus, but now this is zero because the flux was zero in the case. And then delta phi is negative. So if this is so, then d phi over dt is also negative. So it means that it's not the regular case, but in opposite case, so the induced magnetic flux will be in the direction of the original magnetic flux. So because the magnetic flux is reducing, so the direction of the induced magnetic field will be also in the direction of the original magnetic field. In order to do this, you have to create a current like that using our fingers, okay? So the current will have to pass through this way, okay? So it will be circulating like that, coming in here and going out there, then this will be plus and minus, always. From positive side goes away and it comes into the negative side. So the polarity is minus and plus, okay? So now, if we keep rotating the whole system around this rotational thing, okay, axis, rotational axis, then what we will see that the electric potential difference or the voltage will be just changing starting from zero because it was zero there, so it will be just sinusoidal. So as a function of time, the electric field and also the current will be like that, okay? Now, so this is alternating current. Alternating current, okay, or alternating potential. So this is AC, in other words, AC, okay? So from this, you can get the epsilon, which is the potential difference by using this analysis. We know that the current is just a function of time, okay? IT, okay? The current from here is not the current that we get original magnetic field, but it's the current that is induced to this loop, okay? This current is different than this current, of course. So this is, now the current is a function of time. And how can we find that? Okay, so first of all, epsilon is given by minus n, okay, times d phi b over dt, or d over dt, ba times cosine theta, but theta is omega t. Don't forget, here, theta is omega t. Okay, omega t. So the angle is related to the angular frequency times the time, okay? Or omega is the angular frequency is just theta over t, okay? So how much angle is changed per unit time is a definition of the angular frequency. Now, as you see, these two quantities are constant in time, but this is the only term which is a function of time. So you can take the derivative of cosine omega t, which is omega times sine omega t with a minus sign, and this cancel this minus sign. So that epsilon will be just given by n b a w sine omega t. Okay, this is the AC potential. This is AC potential. Okay, this is just the potential, which is a function of time. Now, if they ask you what is the average potential, average potential, okay, during one period. How do we do this? It's very simple, okay? So to get average potential from time changing function, what we have to do is that we have to integrate this from over a period, okay? So in our case, we have this and divide it by the period, and this gives you epsilon average. This is how you define the average electric field, or just the potential. This is what the multimeter measures, okay? So now what we do is that we put now sine omega t here because the rest is just the constant. So now 1 over t times sine omega t dt from 0 to t will give you this, okay? 1 over t, okay? Now the derivative of cosine is sine, so that it must be cosine with a minus sign. So the result is this 1 over omega times cosine omega t, and from 0 to t, and don't forget omega is equal to just 2 pi f or 2 pi over t, okay? Omega is just 2 pi over t. Let's write it like that, 2 pi over t, because we have this period here. Now, if you put the upper boundary, it's just 1 over t, omega, which is 2 pi over t, 2 pi there, t, this t will cancel that one, and then now cosine, if you insert t here for time, it cancels, we get cosine 2 pi minus, okay, cosine 0, because the lower limit is 0, cosine 0, okay? But now what happens is that this is just cosine 2 pi is, and cosine 2 pi cosine 0, okay, you get just 2 here, just, okay, 2, no, let's see, right, cosine 2 pi minus cosine 2, and we have 2 pi, okay. So let's see what cosine 0 is. So the cosine of angle theta, say this is theta, okay, cosine is here, cosine 0 is 1, but cosine 2 pi is again 1, this is going to be 0. So in one period, this will be totally 0. But now, if you get this RMS value, okay, epsilon RMS value, which is given by that. So you take the square of epsilon and integrate from 0 to t, and we get the average and then get the square root. So this is called RMS value. If you put, instead of sine omega t, if you put sine square and then just integrate, you see that the result will be given by just 2 over pi. This is the RMS value. So RMS value is different than the average value. The average value is 0 because, as you see from one period here, this is one period, okay? This is one period in time. So this plus part is exactly the same as minus part, and they cancel each other. This is the reason that the average gave us 0. But now RMS value, which is root mean square. So you get the square and then get the mean of it. The mean means this integration, and then take the square root. If you do this, you will see that the answer is going to be just 2 over pi. So RMS value is 2 over pi for this sign, and then epsilon RMS then will be equal to NBA, okay, NBA times omega, okay, 2 there, and divided by pi. So this will be the RMS value of the potential difference between the two terminals. Now, if we want to get the current, then we have to really specify the resistance of this wire system. If it is given, then we can easily find the resistance, no problem. But now, let's look at this numerical example. Let's look at the numerical example. So they say that the potential difference between the two ends is 120 volts. So this is desired potential difference, okay? We would like to get 112 volts, and we are using 500 turns, then what would be the speed of rotation or rotational speed? What would be W, in other words? Or what is the frequency of this rotation? This is what they are asking. So in order to produce 112 volts out of 500 rotation or 500 windings, so how can you do this 500 winding like that? So we can go and do this and then keep going like this, okay? So we keep going like that, okay? Of course, these cables are not touching each other, or if they are touching, they have to be coated by some material so that there is no physical contact, and then you can continue like that. So as you see, there are many windings that we created. So, but this is 500. So how can you do this? It's simple, because if you have a box like rectangular cross section like that, choose a box and then put the wires around them like that, like that. As you see, not necessarily this will be, these wires will be exactly aligned with each other, and the magnetic field is passing through there, and the magnetic field is passing through there. So you can do such kind of system to produce electricity. But now let's see what kind of number we get for this rotation frequency. So the area is just a squared. One side is given for this problem, and a is just 10 centimeters. So it's a square. If it is 10 centimeters, then the area is just 0.01 meters square, okay? And then from this, we can get B value is given as 0.2 Tesla. B is 0.2 Tesla, so that this 112 is equal to 2 times 500, okay? B is 0.2 times area, which is the square of this, just as you see, this 10 to the minus 2, square root is 10 to the minus 4, and W is there. This is the quantity to be found, and divide by pi. Okay, if you just get W from this expression, you see that it's just 176, and the unit is, of course, radians per second. But now, since this is equal to 2 pi f, from this the rotation frequency is obtained, it's just 28. So it means that in 1 second, we have to rotate 28 times. It's not really very slow process. It must be very fast rotation, as you see. In this case, you can get 112 volts. But suppose that in 1 second, you get only one rotation. Then you have to divide this number by 28, which will be giving you maybe some kind of about 3 to 4 volts or something like that. So okay, if it is slow, but still you can get some kind of voltage, provided that there is a magnetic field. If there is no magnetic field, you can do nothing. If you're just rotating this, getting nothing. So the key issue is that in order to get voltage, you need magnetic field. Or in order to get electric field, because the voltage is related to the electric field always, in order to get electric field, you need the magnetic field. So this is the basics of the Faraday's law of induction. Okay, so now we completed this example. We would like to go to another one, but we don't have enough time. So we will see next time slide Y. Okay, slide Y. Slide Y generator. So in the slide Y generator, what we will have is that we will have a rail this of metal wire, and then this end is totally closed, and we will have a metal rod, and we will move this to the right. This is all metal, so that as you see there is a loop here, and we apply a magnetic field downward somehow, okay, and the area vector is going to be also downward, so that it will be parallel to the magnetic field. So when this rod is pulled, we will see that there is a potential difference between point A and B. So if you put a multimeter or connect a multimeter here, if you pull this to the right, you will see some kind of voltage induced in this metal, although it's not acceptable in physically, because the metal potential difference on the metal is always constant, right? Because we have seen that the potential at a metal is constant, because the metal is just a short circuit. But if you move this in the when there is a magnetic field, okay, if you move the whole system in the magnetic field, you can still create some kind of induced electric field between the 2 points. Although physically it's impossible for the stationary cases, but when it is moving, it can be obtained. Okay, so there will be some electric field between these 2 points, or just the potential difference. It's moving. So now we will see how the mechanism works and how the system works. But now what we will also see is that when you try to pull this to the right, there will be some kind of force totally in opposite direction. So there will be some kind of resistance. So it's not going to be so easy for you to pull this, okay? So once you try to pull, the force will try to, cancel your effect. So you have to really apply a force to do this in order to create some kind of potential difference. But now we will also see the motion of one charge inside, and we will see that the magnetic force will be in upper direction and the electric force will be in lower direction, or just this direction, and they will be balancing each other, so that the force, the whole rod doesn't move up and down, but it moves only this way. So by using this is a really excellent system, because now not only you can see the relationship between the magnetic field and also the induced potential difference, but also physically you can get the force which is in opposite direction. You can calculate this force as a function of the other quantities, and then from this you can find the power that you have to apply in order to pull this rod by using a rope, maybe. Okay, so this is a really excellent example. Usually we ask some questions in the exam, this kind of questions in the exam. So this is very important. Okay, so don't forget about the difference between the two cases. The average of sine is 0, but the RMS is not. But now let's see how to get from AC to DC. So as the last thing I would like to mention this. Suppose we have this AC generator. So our voltage is going to be like this, sinusoidal changing in time, right? So can we really get some kind of DC? So this is AC. We would like to get a DC voltage, because like to fill the battery of the electric car, for instance, we need a DC power supply. Can we really get from AC DC like that? Almost not changing, almost constant, with very, very little ripples. Okay, can we do this? The answer is yes. So this is called AC to DC converter. Okay, so now this is a physics course, but for those of you who are majoring in electronics or also interested in electronics, this is an interesting subject. Suppose you have this power supply, which is AC, and then V in is the power supply here. So now, if you pass this from a bridge of diodes, I will tell you what the diodes now are now, okay, like that. Okay, you connect 4 diodes like this, okay, such that this part produces plus and this part produces minus, okay. So now, if you look at here, the potential is this way, okay, V in is like sinusoidal, totally AC, as you see. But if you look at here, you will get the potential like this, okay. So at this part, the potential will like this. So the negative parts will be flipped over, and then you will get this kind of behavior, okay, for V out. But now this is not really AC, DC like that. But how can we get DC out of this is to connect a capacitor. Okay, if you connect a capacitor, now we know that this part will fill the capacitor. So the capacitor is filled, and then it's trying to go down, but not finding enough time to go 0 volts. So another bump is coming, and then it's going like that. So it's all going up and down. It's like a ripple, but it's almost constant. Okay. So the value of this capacitor, when the value of this capacitance increases, the amount of ripple reduces, and then you get very straight line. So this is rectifying. This is rectifying. This is rectifier circuit. Okay, the whole thing is rectifier. So we are able to obtain now a DC voltage. So this is V out, and V out is this. V out is this after passing through the capacitor. But before capacitor, it's just that, and after capacitor, the voltage is like that. So you get DC from AC by using diode. And the property of the diode is that it's a semiconductor, and then this is called the barrier part is cathode, okay? This part is anode, okay? And the current is okay to pass through this way, but not okay this way. Why? Because this looks like a barrier, as you see. So when the current attempts to pass from this side, there is a barrier so that it cannot go. So the direction of the current passing through this way is allowed, but not that way. That's why when this signal is positive, it passes from this part, and of course, this one comes again here, okay? But if this is negative, then the negative part goes from this, and then we get again plus there, always, okay? Regardless of the sign of it. So this is bridge connection, the bridge connection, very famous, okay, in electronics. It's used everywhere. So instead of using 4 diodes now, there are some devices which are called bridges. It's like cylindrical in shape, and there are 4 wires like that, and one is plus and the other is minus, and this is like the other 2 is alternating source. So if you connect this one in the back and this one, the AC signal, this signal, and then you can get plus and minus 1 like that. So it's just one unit is including 4 diodes, and it's just very cheap. So this is like about maybe 50, okay, 0.5 Turkish lira or something like that. Very, very small amount of money. Anyway, so this is very interesting. Now you're really getting into the electronics, but now this is the basics of motors, and the Faraday's law of induction is extremely important. Okay, so I hope that you understand this. Next time we will complete this chapter, solving more and more examples and giving really very interesting systems, defining very interesting systems like this, like slide wire generator. Okay, this is the end of the lecture.